Hello everyone. Welcome to the third lecture of this course on reinforcement learning. I'm Dhiraj Madan, and today we'll be continuing with our discussion of policy evaluation in Markov decision processes. So, in this course so far, in the past two lectures, we have seen Markov decision processes as a way to formalize reinforcement learning. So, reinforcement learning is nothing but learning from feedback. In order to formalize that, Markov decision processes are designed as follows. So, they consist of a set of states or a set of configurations in which a system in which an agent can be in. So, this is known as the state space. Then there is a set of possible actions or the possible choices which an agent has at every step, which is known as the action space. There is a set of rewards, and an agent can get a positive or negative, a real reward at every state. So this is given by the reward function. The reward function can also be a function of both state and action, or it can be a function of state as well, just a state as well. Uh, and essentially, there is a notion of transitions. So, given a state and action or the choice which an agent makes, the agent moves to a new state. Both, so this is known as the transition distribution, the distribution over the next state given the current state and the action chosen. Both the rewards and the transition distributions are governed by something known as the environment, and the agent has access to its set of actions. What our goal is to maximize the cumulative sum of rewards. The cumulative sum of rewards, we essentially weigh them, by an exponentially decaying term, gamma to the power t. So gamma is some discount factor. Discount factor is typically less than 1. And essentially the idea is that, our goal is now to maximize this quantity. And the idea, why we introduce this gamma is that because we want to get an upper bound on the sum, and secondly, in more economic terms, it accounts for inflation. So the way the trajectory of an agent evolves is that an agent starts in some initial state S naught. It receives a reward R naught. Based on the state S naught, the agent can decide to pick some action, say A naught, as a function of S naught. And based on the action chosen and the current state S naught, the environment moves it to a new state S1, whose distribution is given by this transition distribution. The environment also gives it another reward R of S1, and then the agent picks its new action A1 conditioned on its current new state S1. So this is how the agent's trajectory is going to evolve in time. And correspondingly, we can define the cumulative reward function, which is sum over t rt gamma to the power t. One then needs to choose the set of actions, right? One needs to decide the policy to maximize this cumulative weighted sum, right? So this is what our goal is going to be in the end. Now let's see how to do this. So we saw this policy evaluation algorithm. So here essentially this expectation is over all the distributions which are going to take place, right? So these are all the policy distributions, pi of et given st, as well as the environment's transitions distribution, which is p of st plus 1 given ATST. Right? So all these distributions we are averaging over in this expectation. So condition from the initial state S naught is S. What is this expectation? That's what we tried to compute. And essentially, we arrived at a very simple dynamic programming equation, which is that, if you start from the state S naught, then essentially V pi of S naught is R of S naught plus gamma times the expectation over the next state S1 given S naught and pi of S naught, V pi of S1, right? So you can write it as, the expectation over S1. And okay, of course, if pi is a probabilistic, then it can also include the expectation over pi. Essentially, this is what we have, or essentially, if pi is a stochastic, then it will also include the expectation over the action A naught, right? And we can in fact expand this equation, that expectation, we can write it as sum over S1, P of S1 given S naught and A naught. Or let's say if we do not want to use the variables S naught and S1 because they represent a specific time step in the trajectory, we can use more generic variables S and S prime. So we can write that V pi of S is R of S plus gamma times sum over S prime, P of S prime given S and A naught. A naught is nothing but pi of S, V pi of S prime, right? So for, if there are modest number of states, then essentially we have modest equations. So we have modest equations in modest variables. Now the question is that does it always have a unique solution? And that's what we now need to explore that. So in general, we have seen that it need not even have a unique sort of solution, right? And we gave a sort of a counter example of a simple two state sort of a Markov decision process, wherein you have a reward of one at both these states, and you keep alternating between the two states with probability one, right? So there is only single action, and that keeps you oscillating between these two states. And we saw that actually there is no solution. It actually makes sense intuitively, because if you intuitively try to think of v pi s for gamma equals 1, then it will also be infinite. So there is no real solution, right? Real numbers are supposed to be finite only. We don't count infinity as the set of rings, right? So if you solve this equation, there is no solution if you solve the above system. But our claim was that for gamma less than 1, there is always a unique solution. And we now need to see why is that the case. So let's get started with that. So what we'll do is that we'll try to write the above sort of equations. We'll try to create an iterative algorithm from those, right? So essentially, we write an iterative algorithm. Solve the system of equations. So how that iterative algorithm is. So actually, the reason we are looking into this iterative solution is that not just because we want to prove the uniqueness, but also because this idea will essentially define the value iterations in general. And the same idea of this iterative step forms the basis of many other reinforcement learning algorithms, and including the deep reinforcement learning ones as well. So let's see why. So the idea is that we try to write an algorithm based on fixed point iterations. So I'll tell you later what these fixed point iterations are. But essentially the algorithm is as follows. So we initialize time step t as 0. And let's say the value function at time step t equals to 0, v0s. We start with let's say 0 for all. We could have initialized randomly also, but taking all to be 0 is also one choice. So that's fine. And now we repeat until convergence. So essentially what our step is that vt plus 1s is then assigned as r of s plus gamma times sum over s prime, p of s prime given s and pi of s times v pi of s prime. So essentially, when I say v pi of s prime, it's essentially the current estimate of v pi, which is vt of s. So this is what I keep iterating until convergence. So we can define some convergence criteria, which is that when this value function, this just when the change for every state is, let's say, upper bounded by some epsilon, we say that we have converged. So this is going to be my iterative algorithm. Okay. Now my claim is that this iterative algorithm will converge, and not just that it will converge, it will also converge to my actual solution of the Bellman equations. So my claim is that for gamma less than 1, iterative algorithm converges to converges to V pi s, right? Basically, the solution of Bellman functions. This is the main idea. And in fact, the idea is that, and in fact, whatever be the starting point, it will always converge to this unique solution of the Bellman equations. And that is what my claim is. So to show this claim, I need to use something, some property which is known as fixed point iterations, some a concept known as fixed point iterations. So actually, I'll discuss that. So essentially, let's say, so in order to define that, we define some, we need to show some concepts. So first of all, what are claims that? So when I say the iterative algorithm converges to V pi s, what I mean over here is VTS converges to V. So that's what I. And essentially, in order to do that, we'll discuss something known as the concept of fixed point iterations. So let T from Rn to Rn be a mapping. So this mapping T is a contraction mapping. So mapping means that it's just a function from Rn to Rn. Okay, I'm just calling it mapping. So this is called as a contraction mapping. If for all xy, what I have is that T of x minus T of y, this distance is less than the distance between x minus y, or maybe less than equal to c times the distance between x and x minus y, for some c which is strictly less than y. So there is some constant such that norm of dx minus dy is less than equal to c times that particular constant. Then we say that this is a contraction. Okay. And the result is that as follows, that so there is a theorem. Okay, so I'll create a separate optional video for you to watch in order to sort of see the proof of this particular theorem which I'm going to state now. For this theorem, what it says is that if T is a contraction mapping, then Tx equals to x, okay, has a unique solution. So first of all, it has a solution, Tx equals to x, and secondly, it has a unique solution. Okay, when we are saying unique solution, we are saying two things. Firstly, that there is a solution, and secondly, that there is no other solution. There is only one solution. Okay. And moreover, iterative algorithm, or maybe the sequence. Let's not even define algorithm. Let's just say the sequence. Moreover, the sequence given by x naught. Next, then x1 is t of x naught, and x2 is t of x1, which is essentially t of x naught. Then x3, which is t of x2, which is t of x naught. Okay. And so on, right? Wherein your xn is t of xn minus 1. I'll need to discharge this pencil. Basically, xn is nothing but t of xn minus 1. So when I say t of xn minus 1 and xn minus 1, of course, t of xn minus 2. So essentially, t of xn. So there are n times applied, and so on. So basically, there is this particular sequence I'm defining. So this converges. So how am I defining the sequence? So I start from x naught, then I take t of x naught, then I take t of x naught, t of x naught, then t of x naught, and so on. So this is how I define the sequence. So this sequence converges to unique solution of tx equals x. Okay. So I have defined a sequence given by, so basically the sequence is given by x naught is some arbitrary and xn plus 1 is t of xn for all greater than equal to 0. Okay. So therefore, for every x naught, the above sequence converges to the unique solution of tx equals to x. So this is what the theorem is. Maybe take a couple of minutes and maybe pause the video to digest the contents of this theorem. We are making a very strong statement. Right? It's not just a simple naive statement. We are making a very strong statement that whatever x you start with, so you will define so many sequences, and all of these sequences are going to converge. Firstly, not just they are going to converge, they are going to converge to a solution of tx equals to x. And we are saying that that solution is also unique, right? So we are saying so many things together. And the proof actually will end up proving the uniqueness also, and it will prove the existence of solution also. We'll actually have a separate sort of an optional lecture I'll have to sort of prove this theorem. For now, let's just see how do we apply this theorem to show the uniqueness of uh, the solution of Bellman's equation when gamma is less than. Okay. So in our case, so if you look at the iterative algorithm I defined over here, so essentially this iterative algorithm, what it is doing is that it's also performing a set of fixed point iterations, right? Why? Because I'm taking this value function, I can just take it as a vector of these values at every state, and I'm applying this sort of Bellman operator on that. So what is that Bellman operator? And I'm getting, the next variable. So we consider, in case we consider the iterative algorithm as a uh, uh, as a sequence where this vector vt plus 1 is this operator t acting on vt. Okay, so vt I'm just considering it as a vector now, as a vector of the values for every state, right? So I just flatten all the states together in a single vector. The vt of s, s, it can take all those mod s values. This is a mod s valued vector. Okay, so that's how I've considered it. And what is this t operator? For t equals to for t of x. So x is a vector, right? And how does it update this vector? So essentially, this vector is essentially for t of p equals to v prime given by v prime of s. So this is a vector, and the updated value it satisfies that v prime of s is going to be r of s plus gamma times sum over s prime p of s prime given s and pi of s, and this much times v of s prime. So basically the thing is that if you know v, this is what TV is going to look like. So TV is going to look like V prime, where V prime of the state S is going to look as follows. So essentially from V, we are going to V prime, right? So this is how we are going from Vt to Vt plus 1, right? So earlier we are applying this operator capital T and we were going from Vt to Vt plus 1. But this is a general sort of an operation we have now defined, which can go from, the value function V to a value function V prime. What does it do? It averages out the values of V using this P of S prime given SPS operator. And then it adds RS and then it gives me V primes. So this is the how the operator is going to look like. This is my mapping T. So TV is V prime, where V prime of S is RS plus gamma times sum over S prime, P of S prime given S by S times P. Now my claim is that so what's my claim is? So the claim is that this mapping T is a contraction map. How do I show that? Well, so let's take two value functions, P and U. Two value functions or vectors. So both of these belong to R to the power minus. Okay. Now, my claim is that let U prime be T of U and V prime be T of P. Okay. And now we need to look at the distance between these two vectors. So in order to define the notion of distance, right, so which is essentially norm of U prime minus V prime, so we let norm of U or the infinite norm of U. So this is essentially the supremum norm. So this is essentially supremum over S and S mod of U's. So I'm defining a particular notion of, right? And under this notion of norm, this is going to be a contraction. So let's see how. So essentially, we need to show that, that norm of U prime minus V prime, that is less than equal to C times norm of U minus V for some C. And it will turn out that that particular C is exactly uh, the discount factor itself. Okay. So, and we have defined this notion of norm. Actually, so you will have to show that this is a norm. A norm should satisfy some properties, and you'll have to show that it satisfies those properties as well. So essentially, those properties are the triangular inequality. Norm of U plus V is less than equal to norm U plus norm V. And then what you have is that norm U is always greater than equal to 0. It's equal to 0 if and only if the vector is 0. And third property is that norm of alpha times U is essentially mod alpha times norm. So it satisfies all those properties. This is called as a sup norm. And now let's see whether under this norm, whether we have a contraction mapping. So let's consider norm of U prime minus. So this is essentially norm of TU minus TV. Right? And essentially, what's that going to be? So TU minus TV is essentially, this is how my V prime is defined. So this is essentially nothing but supremum over all the states. Right? So this infinite norm is what we are taking of U prime minus V prime of S. This is nothing but supremum over all S mod of U prime S minus V prime S, which is supremum over all S, R of S, okay, plus gamma times sum over S prime, okay, and P of S prime given S and pi of S, okay, and U of S prime. So this is nothing but U prime of S. And V prime of S is going to be R of S plus gamma times sum over S prime, P of S prime given S comma pi of S, and V of S prime. This mode. This is nothing but supremum over S. And now I have gamma I can take outside. And I have sum over S prime P of S prime given S and pi S times U of S prime minus P of S prime. Okay. And now I'm going to use triangular inequality. So there is a summation and there is a magnitude outside. So essentially from triangular inequality, we know that mod of A plus B is less than equal to mod A plus mod B. And we can always generalize this to n quantities also. Mod of A1 plus B2 plus B2 plus up to Bn is less than equal to mod of A1 plus mod of A2 plus B2 mod of A. So I can say that this is less than equal to supremum over S. And actually gamma can come outside the supremum. So it's gamma times supremum over S, sum over S prime, and mod of P of S prime given S pi S times this thing, right? But P of S prime given S pi S is also non-negative, so that can also come outside the mod. And I have nothing but U of S prime minus V of S prime. Okay. And now what I do is that, so this is supremum over all S of this quantity. So I need to choose one S, which maximizes the sum. So what I do is that I independently maximize each quantity. And then let's see what's happened. Okay. So let's essentially write it down. So each of these quantity, right? So whatever S you pick, okay. Now we know that for all S, okay, this particular quantity, so gamma times sum over S prime, P of S prime given S pi S times U of S prime minus V of S prime. So this is less than equal to gamma times sum over S prime P of S prime given S and pi S. And this is always less than equal to U minus V the infinite, because that's the supremum over S prime, U S prime minus V S. And then this quantity sum over S prime P of S prime given S pi S, right? So this is now independent of S prime and S as well. And this quantity, when if you sum over S prime for a fixed S, this is nothing but 1. So this is less than equal to gamma times norm U minus V of infinite norm of U minus V. So this is true for every S. So even the supremum over S is also satisfied, right? Because for every S I have found an upper bound, and supremum is the least upper bound, which is going to be less than equal to any upper bound. So this is now less than equal to gamma times the U minus V the infinite. So for gamma less than 1, what I have done is that I have found a sort of a way to upper bound this U prime minus V prime norm with gamma times U minus V. And this essentially shows that the infinite norm of U prime minus V prime is less than equal to gamma times the infinite norm of U minus V. And gamma is discount factor, so this is less than 1. Therefore, the mapping, so Tu equals to U prime is a contraction. And if it is a contraction mapping, essentially using the previous theorem, what we can say is that what this algorithm is doing is that it's exactly running the same sequence which is defined by that theorem, right? Because what I'm essentially doing is that I'm defining Vt of S as T of Vts, right? And T is a contraction mapping. So essentially this algorithm itself is giving me a sequence of these vectors or value functions, modest size vectors. And this sequence of these vectors is going to converge to a solution which is a solution of Tx equals x. Therefore, the previous algorithm by earlier theorem our iterative algorithm converges to the unique solution of EV equals. So what is that solution going to satisfy? That solution is going to satisfy that V of S is R of S plus gamma times sum over S prime, P of S prime given S pi S, V of. So essentially that is, so if we satisfy the system of equations, we have essentially solved the Bellman equation. Essentially, therefore, this shows uniqueness and existence of solution to Bellman equations for gamma less than 1. Okay. And okay, so not just okay, so but essentially, and it also gives us a new algorithm to solve the system of equations. So let's just discuss that as well. So if you solve, in general, if you solve a system of n variables and n equations, exactly. So okay, so the standard Gaussian elimination algorithm will take order n cube time. There are more efficient algorithms as well. But you know, the more commonly used ones for exact algorithm, for exact solution, is this Gaussian elimination. But essentially, if you want to solve it approximately, so you can actually use the iterative algorithm for Bellman equations, right? Not for every system of equations, for you know, the system of equations wherein you have that system defined by contraction mapping. For example, in Bellman equations, it is. Then you can also use the same iterative algorithm which we defined at the beginning of this lecture. And that algorithm will also form the basis for value iterations, which we'll discuss in the subsequent lectures. Also, one more thing is that I had earlier mentioned that you know, the when we derive this sort of Bellman equations, we assume that pi is deterministic, right? And I asked you to you know, prove it as a homework exercise, or to you know, obtain the Bellman equations for stochastic conditions as well. I think I wanted to give it as a homework exercise, but in any case, let's discuss that now. Okay, so if you haven't tried it, I would ask you to you know, first pause the video and try it yourself. If not, if you have it, then let's discuss it as well. So essentially, when we you know, try to compute the sort of those Bellman equations, so we said that this is an expectation over pi and expectation over the transitions P of S prime given AS, sum over T RT gamma to the power T. And essentially what we said was that we can take R naught, or R of conditioned on S naught is S. So we can take out R of S outside, and we had this gamma, and what we were left with was that we had expectation over pi of firstly A naught given S naught, and okay, so this is A naught coming from pi of A naught given S naught, and S1 coming from P of S1 given A naught and S naught. And we have that this quantity T from 1 to infinity RT gamma to the power T minus. And we could say that this was essentially, there was the expectation over everything else, right? Pi of 2t given st and p of st plus 1 given st. So we had conditioned on S naught is S and S1 is S, or S1 is S prime. So, okay, let me rewrite it. It's too clumsy now. So essentially we had broken this expectation into two terms, two expectations. So first we were taking the expectation of A naught coming from A naught given S naught, and then S prime as P of S1 equals S prime given S naught is S and A. And the second expectation was over AT as pi of AT given ST. So this is of course R of S naught is outside and comes taken out. So pi of at given st, and st plus 1 is coming from p of st plus 1 given st at. Okay. And then we have sum over t rt gamma to the power of t minus 1, t of 1 to infinity, given s naught is s and s1 is s prime. So earlier, when a naught was deterministic, we could easily solve it. As we just wrote it as sum over s prime p of s prime given pi of s naught times v pi of s prime. So we can actually still do it in a similar manner, because this initial term is still essentially v pi of s prime. But now this expectation is over expectation of both a naught pi of a naught given s naught and s prime is just p of s1 equals to s prime given s naught is s and a. Right? And this inner quantity is just v pi of s. V pi of s prime. Okay. So this is r of s, right? Because s naught is s. So essentially, in general, if what we are trying to discuss is that what if a naught is, what if pi is stochastic? Essentially, we'll have to average over this a naught, okay, where a naught comes from pi of a naught given s naught, and you will have to average over s prime, where s prime comes from p of s prime given a naught and s, and v pi of s. So your new sort of Bellman equations where pi is stochastic is going to look like this. For stochastic policy. Okay. So that's it for today's lecture. In the next lecture, we will discuss the so in the next lecture we'll discuss the algorithm for so in the next lecture we are going to discuss the proof for the fixed point iteration. So okay, thanks a lot. Hope you liked today's lecture. Bye.